Okay, so this is where we left off last time. And what we're going to do is we're going to do an example of computing complex power here. But before we do that, we have one other thing we should discuss briefly here. I'm not going to go in a lot of detail on this. I mean, it's basically um, looking at these cosine of theta v minus theta i's. If we have what's called a lagging power factor, that means the current lags behind the voltage. We have what's called an inductive load. And how do we know that? That's purely going to the idea of looking at your impedance equations and the voltage current relationship for an inductor, and the fact that you have the impedance of an inductor being j omega L. And then if you have a leading power factor, this means that the voltage lags the current, and we have a capacitive load. And again, that's just looking at the equations. But the one thing I want to point out here is, for instance, if you have power factor being positive here, reactive factor is also positive, because basically if you're an inductive load, you're in quadrant 1. If you're a capacitive load, you're in quadrant 4, so your power factor is going to be positive, but your reactive factor is going to be negative. So that's really all that's referring to. So nothing too critical, but it does come up occasionally on some problems. So let's look at an example problem here. So we have an electrical load operates at 240 volts RMS. The load absorbs an average power of 8 kilowatts. With a lagging factor of 0.8. So we're going to find the reactive factor, find Q, and then find S. Really, this could just be a problem that says find S, but the steps would be to find the reactive power factor, find Q, and then we find S. Alright, so how do we get the reactive factor? Well, remember, we wrote this equation in one of our lessons. We haven't really used it yet, but power factor squared plus reactive factor squared is equal to 1. So we know here that we have, for instance, 0.8 squared plus reactive factor squared is equal to 1. So reactive factor is equal to plus or minus the square root of 0.36. Now we know which one it is because it's lagging. That means, again, remember we're in quadrant 1, so my reactive factor is simply a positive 0.6. So real easy to find the reactive factor in this case. And then to find Q, well, we know that sorry, here I lost my train of thought here. We can figure out Q if we know what Vm Im over 2 cosine of theta v minus theta I. Right? Not cosine, sine. But that means Q is simply Vm Im over 2 times my reactive factor, which I should also write the other equation down, because remember, this is also effective voltages or RMS values. Well, remember, we have the same equation for power, roughly, and so we get power Vm Im over 2 cosine of theta v minus theta I. But remember, this here is just my power factor. And also that we could write this as an effective voltage times an effective current times my power factor. Now the reason I'm making sure is we have to go back and see what we're given in the problem. So we're given 240 volt RMS. So that means this is an effective voltage that we are given. So we know that the average power here is 8,000 watts, 8 kilowatts. So we have 8,000 watts, and we're given an effective voltage, so that's equal to 240 times I effective times my power factor, which is 0.8. And so then doing that, we can get that my effective current is 8,000 divided by 240 divided by 0.8 is 41.6 repeating amps. And so then Q is simply, well, 240 times 41.6 repeating times my reactive factor, which is 0.6. So multiply that by 240 and multiply it by 0.6, and we get 6,000 var, or we could write this as 6 kilovar. And so then what we could do here is again just write my complex power down, which is just Q, I'm sorry, not Q, P plus JQ. So my complex power would simply be 8 plus J6, and now the units for complex power is volt amps, so I'd have 8 plus J6 kilovolt amps. And again, the reason we have all these different units is so that we can keep things straight. So if you see just a volt amp, that's usually referring to a complex power. Volt amp R, reactive power. Watts are average power that's actually useful to us. Now we could also convert that to polar. I'm not going to bother. Alright, so that was a quick, easy example, but that's all I'm going to cover here in this video. We're going to kind of start to slowly build up to why we're using these complex power.